One of the most important observatories of planets and stars ever built in the Middle East was established in Baghdad in the year 1259. It was done so under the orders of a Mongol ruler who destroyed the city just a year earlier. This is a reminder that history is rarely as neat or tidy as we might like. So let's train our sights on astronomy and astrology during the Islamic Golden Age, the 5 centuries between about 750 and 1250, and try to sharpen our focus on the work of 3 Islamic astronomers. The first of these is the mathematician al-Khwarizmi, who worked in Baghdad's House of Wisdom during the early decades of the 9th century, and from whose name we derive that most contemporary of computing terms, algorithm. The second name is the founder of modern optics, al-Haytham, who flourished in Cairo, the capital of the Shia Caliphate in North Africa during the first half of the 11th century. And the third is the learned astronomer al-Tusi, who is said to have been present during the fall of Baghdad in 1258, and who oversaw the new observatory that the conquering Mongols ordered built. Al-Tusi was a prolific author whose contributions went well beyond astronomy to include mathematics and what we now call chemistry, physics and biology, including a theory of evolution that predates Darwin by 600 years. He was one of the most important and influential scholars of the Golden Age. Without giving too much of the story away, it's possible that one of these Islamic astronomers played a part in the demise of Baghdad, that center of knowledge and power that had served as the seat of the Muslim world's largest empire at the time, home to the Sunni Muslim Abbasid Caliphate. Now, one reason why the Islamic Golden Age was such a fruitful period for astronomy was because of the conquests that Muslim armies had achieved in the 7th century. Starting in Muhammad's lifetime, the armies of Islam conquered Arabia, the largest peninsula on earth. From there, they took much of North Africa and bits of Europe. Ultimately, they consolidated their power and the Muslim faith from Syria and Mesopotamia, or modern Iraq, to Persia and on into Central Asia, as well as further east to the borders of China and south to India. For the first time in history, the collective wisdom of different civilizations was brought together in one center of scholarship and learning known as Baghdad's House of Wisdom. Established by the semi-legendary 5th Abbasid Caliph Harun al-Rashid before his death in 809, the House of Wisdom became the greatest nucleus of learning on earth. The concentration of so many different intellectual traditions was a spur to all fields of artistic and scientific research and advancement, not just astronomy and maths. Now, given the technological limitations of astronomy prior to the invention of the telescope in the Netherlands in 1608, it's important to be clear about the difference between astronomy and astrology, though both were quite important during the Golden Age and to every civilization that predated Islam. Astronomy is a branch of natural science that looks at celestial bodies beyond the Earth's atmosphere, including galaxies, stars, planets, moons, asteroids, and comets. As a branch of natural science, it relies on observations and other empirical evidence to establish facts about the natural world. Astrology, on the other hand, is what we think of today as a pseudoscience. The adherents of astrology claim to be able to divine anything from an individual's personality to future events, although the way they do so resembles the astronomer's craft, supposedly by studying the movement and relative position of the planets and other celestial bodies. With a history stretching back to Mesopotamia around the year 2000 BC, and perhaps even earlier, astrology has an ancient pedigree in human history. It was important to pre-modern societies as a means of explaining or attempting to explain events on the celestial level. I should also note that for most of human history, astrology was considered a serious scientific pursuit and often went hand in glove with astronomy, medicine, and meteorology. Some of history's greatest minds, when not discussing interplanetary movement, were busy drawing up star charts for their employers, even though some of these wise and venerated men also recognized astrology as hooey, even at the time. Today, astrology is largely confined to the horoscopes one finds along crossword puzzles and the cartoons, as another form of essentially harmless entertainment. But I'm getting ahead of the story. Let's go back to the early days of the Islamic Golden Age to see the corresponding roles of astrology and astronomy then. The Arab conquest of Persia from 633 to 651 was the most important early driver of astrology and astronomy in the Muslim world. Muslim caliphates, starting with the Umayyads, who reigned from Damascus between 661 and 750, followed by the Baghdad-based Abbasids after 750, started adopting certain Persian practices. Not the least of these was the use of astrologers to determine the most auspicious date for important undertakings. This could be anything from the best date for a caliph's wedding to the start of a military campaign, or when to break ground on the construction of a new city, as with Baghdad in 762 and later in Cairo in 969. For Islam's first 200 years, the Muslim world was busy assimilating astronomical and astrological data and customs from three distinct cultural arenas, namely Persia, India, and the Hellenic or Greek-speaking world. At this stage, there was little or no original work done by Muslim scholars, but rather a slow movement towards translating earlier ideas and learning how other civilizations had used astronomical observations for religious and political purposes. During these early years, a court astronomer typically was responsible for drawing up star charts for the caliph and sometimes other high officials. As a result, the court astronomer was a figure of enormous importance and sometimes influence. And then we come to the founding of the House of Wisdom in Baghdad. From that moment on, Muslim astronomers, Persians and Arabs alike, began to produce original scholarship to advance the field, starting with the brilliant and prolific scholar mathematician Al-Khwarizmi. Al-Khwarizmi is best known for his original contributions in the field of mathematics, notably algebra, which word comes from the title of one of his books, and algorithms, an algebraic process taken from the Latinized version of his name. In 830, Al-Khwarizmi published a book called Zij al-Sind Hind, or Astronomical Tables from India. Zij was the general Persian term for the astronomical works that contained tables detailing the position of the sun, stars, and the 5 planets then known to astronomers: Mercury, Venus, Mars, Jupiter, and Saturn. Without wishing to confuse matters, I should say that classical astronomy, including Greek, Babylonian, Persian, Norse, and others, counted 7 planets, the 5 I just named, plus the sun and the moon. Now, while the sun and moon are not planets as we now define them, these 7 celestial bodies gave us, through Roman astrology, the names of the days of the week. Al-Khwarizmi's Astronomical Tables from India was the first original work of Muslim astronomy and a turning point. Until then, Muslim astronomers had merely adopted the work of others via translation. Now, thanks to Al-Khwarizmi's inquiring mind, new research and new celestial observation, along with calculations using new mathematical principles, led to a mass of original findings. While no original Arabic edition exists, we do have a Latin translation of Zij al-Sind Hind, thanks to one Adelard of Bath, the great 12th century scholar whose travels in the Near East brought him into contact with Arabic science. More than 800 miles west of Baghdad, and nearly 200 years after al-Khwarizmi's death, around the year 850, another important astronomical text was written in Cairo by the father of modern optics, Ibn al-Haytham, who is generally known in the West as al-Hazen. Cairo was ruled then by a Shia Muslim entity that had risen as political rivals to the Baghdad-based Sunni Muslim Abbasids. Known as the Fatimid state, it originated in North Africa and is often referred to as a shadow caliphate for the period of its reign, which was from 909 to 1171. Al-Haytham, born in around 965 in the Iraqi city of Basra, moved to Cairo sometime around the year 1000, and it was there, in Cairo, that he did most of his important work. In all, he would author some 200 scholastic treatises, of which some 25 dealt specifically with astronomy. Like al-Khwarizmi, Ibn Haytham is arguably better known for his work on theoretical physics and optics, although light and seeing are also central to observing the planets and other celestial spheres. That said, Ibn al-Haytham made a revolutionary break from earlier traditions by positing the idea that scientific hypotheses, to have any meaning or value, must be provable and rely on mathematical and/or demonstrable experimental evidence. As such, Ibn al-Haytham is widely considered to be one of the first theoretical physicists, and he was widely known in medieval Europe around the 13th century as the Second Ptolemy. Now, being called the Second Ptolemy isn't without a tinge of irony, since al-Haytham's most famous astronomical work is a treatise called Doubts Concerning Ptolemy. Until then, Ptolemy's book Almagest, about the paths of the planets and stars, and written in the 2nd century AD, had been the single most important astronomical work to survive from ancient times into the medieval world. Incidentally, Almagest isn't Ptolemy's original title, but rather the Arabic name it acquired during the Golden Age. It means Al-Majesty, or the greatest in Arabic. It was this book, and two others by Ptolemy, Planetary Hypothesis and Optics, that Ibn al-Haytham attacked as flawed. Almagest is a mathematical and astronomical treatise in which Ptolemy posits a geocentric model of the universe, one that was accepted as self-evident for 1200 years, in spite of the fact that it was wrong. As we all now know, the Sun and not the Earth is at the centre of our solar system. But no matter. Ptolemy was almost universally accepted by scholars in ancient Greece and Rome, the Muslim Middle East and Christian Europe, until his theories were finally and completely overturned, when the Polish mathematician and astronomer Nicholas Copernicus published On the Revolutions of the Heavenly Spheres in 1543. Ptolemy himself had pointed out that there were contradictions in his writings, but he said they didn't matter terribly, hardly an approach that would meet modern scientific standards. Yet no scholar keen to protect his reputation would have challenged Ptolemy's authority back in the day, though some people had their doubts even before Copernicus, al-Haytham being one of them. So on what grounds did al-Haytham challenge Ptolemy? Well, he began by highlighting the contradictions inherent in Ptolemy's three great astronomical works, Almagest, Planetary Hypothesis, and Optics. Now, challenging the work of others is not the same as having all the answers oneself. Like Ptolemy, al-Haytham was wrong in placing the Earth at the centre of the solar system, And both men were also wrong in assuming that the planets made a perfect circular motion around whatever body they orbited. Copernicus addressed the first of these misperceptions when he published his heliocentric, that is to say, sun-centered as opposed to earth-centered, model of the solar system in 1543. Later, between 1615 and 1621, the German mathematician and astronomer Johannes Kepler published his own theories on planetary motion, including the theory of elliptical orbits. Among other things, Kepler's laws of planetary motion explained away how planets appeared to change speed when they are thought to be moving in a perfectly circular orbit. Some might minimize Al-Haytham's importance, because while he set out to correct Ptolemy's errors, he ultimately failed to do so. But this would be to miss the more important point. Al-Haytham was honest about the difficulty in gaining scientific knowledge, while also clear about the importance of challenging the masters in trying to do so. He wrote, "Truth is sought for itself, but the truths are immersed in uncertainties, and scientific authorities are not immune from error." In other words, he was saying that it's right to challenge received wisdom and existing theories, even if one can't provide all the answers. Only through such challenges can scientific growth emerge. Now it's time to continue our journey through time to meet our third astronomical giant of the Islamic Golden Age, Muhammad ibn Hassan al-Tusi. He's actually better known as Nasr al-Din al-Tusi. The term Nasir in Arabic means helper or one who gives victory, while al-Din refers to the religion, i.e. Islam. That's a way of saying that al-Tusi became known as the one who gives victory to religion. This is clearly a mark of his importance among scientists from this period, as well as a clear sign that there was no inherent contradiction between religion and science in al-Tusi's day. As for his family name, al-Tusi, that simply means someone from the ancient city of Tus in northeastern modern-day Iran, towards the borders of Turkmenistan and Afghanistan. The city of Tus is also the birthplace of the 10th century Persian poet Ferdowsi, the critically important 11th century Muslim theologian Al-Ghazali, as well as the place where Harun al-Rashid, the Abbasid caliph who founded Baghdad's legendary House of Wisdom, died in 809. Al-Tusi was born into a Shia Muslim family in 1201. His father died while he was still young, but fulfilling his father's wish that he got a good education, he didn't interrupt his studies. Instead, he travelled widely to learn under the best teachers available in Greater Persia. And by the time he was a teenager, Al-Tusi's skill in the study of the Quran, mathematics, and philosophy had been noted. His contemporaries include the English philosopher Roger Bacon and the Dominican friar, philosopher, and theologian St. Thomas Aquinas from modern-day Sicily. In all, Al-Tusi wrote more than 160 titles, of which 25 were in the Persian language. The remainder were written in Arabic. Now, not all of these books survive, but their titles show us that he wrote about the Quran, hadith studies or commentaries on Muhammad's sayings, and Islamic law, as well as on the so-called ancient sciences, which incorporated Greek philosophy, mathematics, and astronomy. He was also known as a brilliant translator and personally produced definitive Arabic language versions of the works of Euclid, Archimedes, and Ptolemy, among others. He is also considered by many to be the greatest astronomer in the roughly 1300-year span between the death of Ptolemy in the 2nd century AD and the birth of Copernicus in the late 15th. Astronomical observations led him, for instance, to reach the following original conclusion about the Milky Way, the galaxy that contains our solar system. Al-Tusi wrote, "The Milky Way is made up of a very large number of small, tightly clustered stars, which on account of their concentration and smallness seem to be cloudy patches. Because of this, it has been likened to milk in colour. It would be another 300 years before Galileo Galilei, using a telescope, eventually proved this cloudy patch theory in 1610. Like his predecessor, Ibn al-Haytham in Cairo 200 years earlier, Al-Tusi was indebted to and grateful for, yet critical of, Ptolemy's astronomical work. He was especially unhappy with Ptolemy's suggestion that regular planetary movement could be explained only if one accepted that planets sped up and slowed down at different stages in what he said was their perfectly circular orbit of the Earth. Al-Tusi also disagreed with Ptolemy in another respect, challenging his logic in essentially arguing that the Earth must be static just because it appeared to be so. Al-Tusi wasn't able to prove Ptolemy wrong on this point. For that matter, he might even have agreed with him. But what he objected to was Ptolemy's lack of evidence as the basis for this supposedly scientific conclusion. Al-Tusi's challenge to Ptolemy and his desire to produce a better explanation for planetary movement saw him come up with one of his more enduring contributions to mathematics, the Tusi couple. The Tusi couple is a device in which a smaller circle rotates inside a larger circle, one with a diameter twice that of the smaller one. In addition, the smaller circle moves in the opposite direction and at twice the speed of the larger circle that contains it. The rotations of the smaller circle inside the larger one cause a point on the smaller circle's circumference to oscillate in a linear motion, for instance from top to bottom, along the diameter of the larger circle. This model seems to allow for the explanation of the motion of the planets as circular and regular. Alas, the Tusi couple didn't work for the movement of the planet Mercury, as Al-Tusi observed it. In this, Al-Tusi was led astray because, like his predecessors, he believed in a geocentric or Earth-centered view of our solar system. In spite of clearly possessing one of the best minds of his day, the path of Al-Tusi's research didn't always run smoothly. On more than one occasion, it seems he promised to provide his royal patrons with a quick answer to some mathematical challenge, only to find that it was not as straightforward to solve as he had claimed. For instance, it was more than a decade before he was able to deliver the Tusi couple to his patron. I typically cite the sack of Baghdad in 1258 as the date the Islamic Golden Age ended. And certainly my choice can be challenged on various grounds, but there's also a lot to be said for it. In the plus column, the destruction of the Abbasids' capital was a blow from which the best scholastic traditions that had prevailed in the Middle East for 500 years arguably never recovered. In the minus column, the sack of Baghdad didn't mark the final end of scholarly research in the wider Middle East, as the story of Al-Tusi makes perfectly clear. The very next year, in 1259, Hulagu Khan, the leader of the Mongols and the destroyer of Baghdad, built a grand observatory in Marageh, in the northeast sector of modern-day Iran. This was after Al-Tusi complained that his astronomical charts weren't accurate enough. Now, why would a foreign conqueror like Hulagu Khan listen to the squeaky wheel complaints of a local scholar about the accuracy of his charts? I have a thought on that, but I'm going to withhold it just for another moment. The fallen Abbasids had previously built observatories in Damascus and Baghdad during the reign of the Caliph al-Ma'mun, who died in 833. These early observatories, according to the contemporary British physicist Jim al-Khalili, who was born in Baghdad, marked the beginning of 700 years of Arabic astronomy and provided the bridge from the Greeks to the Copernican revolution in Europe and the birth of modern astronomy. The legacy of Golden Age astronomy can still be seen in the names of lunar craters, asteroids, stars, constellations, and more. Al-Khwarizmi, Ibn al-Haytham, and al-Tusi are all considered important enough to have craters on the moon named after them, names that are approved by the International Astronomical Union. There are also more than 20 other Muslim astronomers and scientists who are honoured in this same way. These include al-Biruni, founder of Indian studies, among other things; Ibn Rushd, or Averroes, the great Andalusian philosopher; Ibn Sina, also known as Avicenna, the Persian polymath; Ibn Battuta, the inveterate traveller; Omar Khayyam, the Persian mathematician, philosopher and poet; and al-Ma'mun, the Abbasid Caliph, whose backing for the House of Wisdom provided impetus for the Islamic Golden Age. And then there are the hundreds and hundreds of stars and other celestial features that carry names bestowed on them by astronomers who worked during the Islamic Golden Age. The best known Arabic star name is probably Betelgeuse. This somewhat odd-sounding term comes from the Arabic Yad al-Jawza, or the hand of the giant. The giant in this instance is Orion, in which constellation we find Betelgeuse. In another prime example of the perils of translating unfamiliar languages, the first letter of the Arabic word for hand, ya, looks similar to the Arabic letter ba, or b in English, and so yad became bad. In time, Yad al-Jawza became Bad al-Jawza, and finally Betelgeuse. Other famous Arabic star names include Aldebaran, which means the follower, Al-Ghul, or the ghoul, Rigel, the foot, and Vega, which means the plunging, as in an eagle. More than 210 stars in the night sky that are clearly visible to the naked eye have Arabic names. So let's close by examining whether the fact that al-Tusi was a Shia Muslim might in any way be related to the sack of Baghdad. Belonging to the Ismaili sect of Shia Islam, al-Tusi was a resident of Alamut, the mountain fortress redoubt of the notorious assassins, when the Mongols arrived in 1256. Notorious throughout the greater Middle East and feared by Christian crusaders and Muslim enemies alike, the assassins were masters of that targeted form of murder now indelibly associated with their name. The Mongols wanted to destroy the assassins' base at Alamut before marching on Baghdad, so as not to have this feared enemy at their back. The story goes that al-Tusi, seeing which way the wind was blowing, betrayed the secrets of Alamut's defences to the Mongols, who rewarded him by sparing his life and making him head of religious affairs in Baghdad after they conquered the city. Putting a Shia Muslim scholar in charge of the former head of the Sunni Abbasid Caliphate is quite a gesture. And then there was that brand new observatory he was given a year later. Certainly makes you think.